I need a lab partner for next semester. Please don't let them be from Jester.
Patience, the Oracle will give you your starting initial, but it first requires an offering of photons.
Little did they know, they weren't just using magic, they were using computational imaging.
Wait, that's it? It looks like a swimming pool. What is this?
Actually, it's working perfectly fine. We're just doing something way cooler.
To understand the Oracle, we have to look inside the box. A normal camera uses a glass lens to funnel light perfectly from one point in the world to one pixel on a sensor. It's a one-to-one map.
The DiffuserCam is different. We've ripped out the lens and replaced it with this, a piece of double-sided tape. This is our diffuser.
Because of the tape's surface is rough and uneven, it bends light in 1,000 different directions. One point of the light from the iPad hits the tape and it explodes into a complex web of ripples across the entire sensor.
This is called multiplexing. Instead of one pixel per point, we have one pattern per point. It looks like a blurry mess to us, but every single vein of light contains hidden information about where the light came from.
So the tape isn't blocking the light, it's just encoding it?
Exactly. It's an optical encoder, and since we know exactly how the tape scatters the light, we can use math to work backwards and uncode the image.
But the computer isn't a mind reader. Before it can decode the seeker's initial, we have to give it the secret key.
That key is what we call the point spread function. By showing the Oracle exactly how it blurs a single point of light, we create a map that lets us solve the puzzle.
Okay, I'm sold. So how'd you actually make this thing? Did you find it in a haunted junkyard?
Not quite. It's more hardware store than haunted. To get the Oracle to work, we had to get the physics just right.
Let's take it apart and see how we built the eye of the Oracle. Step 1. We removed the standard lens. Without glass to focus on the light, the sensor is essentially blind until we add the diffuser.
We used double-sided tape because its thickness and adhesive texture create a beautifully complex scramble. We had to maintain a precise distance, about 3 millimeters, between the tape and the sensor.
This distance is critical. It determines the size and sharpness of the cosmic patterns. Too close and the patterns are too small to see. Too far and the light gets too dim. To understand the blur, we first need the point spread function, PSF. This is the key to our lenses system.
What is this? It just looks like more ripples.
That's our point spread function. It's a snapshot of how our specific piece of tape bends a single point of light. Since we know this response, we can use it to translate any other image the camera captures.
Finally, the math. We don't just take a photo, we reconstruct it.
We use a method called alternating direct method of multipliers.
The computer looks at the blurry mess, compares it to our PSF key, and iteratively guesses what the original object looked like until the error is minimized.
We built this local web app so you can use the DiffuserCam seamlessly. All you have to do is take or choose your calibration image and then take the photo. Both your calibration and image grayscaled RAWs will appear on the screen, and you can watch your image be reconstructed with the iteration number of your choice. Images are saved automatically in your choice of grayscale or color.
Wait, look at that screen. The squiggles are moving.
That's the algorithm at work. Every iteration, the image gets sharper.
It's solving thousands of linear equations simultaneously to find the most likely shape of your initial.
There it is! It's an A! Wait, does that mean my lab partner's name starts with an A?
Maybe the Oracle is just telling you that you're low. Or maybe it stands for absent, as in you're absent from the class roster.
So we went through all this math just for the Oracle to roast me?
Hey, the math doesn't lie. It just gives you the raw truth.
Jokes aside, what we've built here is more than just a roast machine. We've proved that you don't need a $500 glass lens to capture the world.
By using double-sided tape and a Raspberry Pi, we've moved the complexity of photography from hardware to software.
This is the future of imaging, from medical endoscopes that can fit inside a vein to ultra-thin lenses for satellites. Computational cameras are changing how we see the invisible.
So the camera might have just called me alone, but at least I have a pretty cool thing to keep me company.
Thanks for watching!